Welcome. This is going to be a brief video on change of basis matrices. So let me recall the setting. You have a linear transformation T from a vector space to itself. And if you have a basis of the vector space, you can write down the matrix of the linear transformation with respect to that basis. And I'm going to use the notation square brackets T sub B to mean the matrix. So this is an n by n matrix. And what is it? Well, you write TV1 as A11V1 plus A12V2 and so on, up to A1NVN. And similarly, you write TV2 as a linear combination of the V's, all the way down to TVN as a linear combination. And that you pull out the coefficients and you get an n by n matrix. And this n by n matrix depends on the basis, which is why I've written it with the subscript B. And today what I want to talk about is what happens if we have two bases. So let's say you're given a basis V1 through Vn, and another basis, say W1 through Wn. And suppose I give you the matrix with respect to one and the matrix with respect to the other. And my question is, how are they related? They must have something to do with each other. How are they related? Or another way to say the same thing is, how do you go back and forth? Suppose I gave you the first one. How could you compute the second? How do you find the basis, the matrix? How do you convert from one basis to another? Okay, well, the only thing to do is an example. So let's see. Let's do the following example. Let's take our basis V1, V2. And suppose I told you the linear transformation in terms of V1. I told you that TV1 was minus V1 minus V2, and TV2 was 6V1 plus 4V2. Sure, why not? So that is to say, I'm telling you that the matrix with respect to this basis is what? Let's just refresh our memory. You take these two minus ones and put them in the first column, and you take the 6 and the 4 and you put them in the second column. That's how you get the matrix with respect to the given basis. Or in other words, if you take this matrix and apply it to 1, 0, you get minus 1, minus 1, and if you apply it to 0, 1, which is to say V2, you get 6, 4. Okay, so that's not a change of basis, that's just remembering how to write down a matrix with respect to a basis. Now let's come along and suppose we had a new basis, W1 and W2. So W1 and W2 are expressible in terms of V1 and V2, so let's say W1 is 3V1 plus V2, and W2 is, let's say, V1 plus V2. And then the question is, could you please tell me what the matrix is with respect to this new basis, B prime? Prime, there you go. So that's, I've got the matrix with respect to B, and I'd like to figure it out with respect to B prime. So I have the essential information written down up here. Let's see, how do you figure out this matrix with respect to V prime? B prime. Well, let's compute TW1. Well, in order to do that, you need to write W1 in terms of V1 and V2. Well, I have that here, so you plug in 3V1 plus V2. And now using the linearity of T, that's 3TV1 plus TV2. And do we know TV1? Well, of course we do. That's given over here, so you plug that in. 3 times minus V1 minus V2. And you know TV2 is also given. That's up here. So that's, you plug in 6V1 plus 4V2. And that tells you TW1, and you can group terms. Minus 3 plus 6 is equal to 3V1, and minus 3 plus 4 is equal to plus 1 V2. All fine and good. But the problem is, excuse me, I need to know TW1 not in terms of V1 and V2, but in terms of W1 and W2. So I'm sort of halfway there. I computed it, but now I have to convert back to the W's. So look up here, I have the W's in terms of the V's. I need to go the other direction. I need to write the V's in terms of the W's. And, well, that's basically computing an inverse matrix. Let's multiply the first equation by 1 and the second equation by -1 and add them, because that cancels the V2's, and you get W1 minus W2 is equal to V1. And let's see, if you multiply the first equation by -2 and the second by 3 and add them, the V1's will go away. So you get -2 W1 plus 3 W2 is equal to V2. So that was a little hasty, but you get the idea. I converted from to compute the V's in terms of the W's, and so now I can write V1. Let's see, I've got 3V1. I now have V1 in terms of the W's, so I can plug that in to get W1 minus W2. And let's see, V2 I've got here in terms of the W's. So I plug in -2 W1 plus 3 W2. And, excuse me, I group terms. 3 minus 2 is 1, so I get 3 minus 2 there. And then, let's see, -3 plus 3 W2. And what I get is simply W1. So now I've computed T of W1 in terms of W1 and W2. So I need to do the same thing with respect to, for W2. I'll do this sort of quickly. You write W2 as 2V1 plus V2. And so you get 2 TV1 plus TV2. And that's 2 TV1 is minus V1 minus V2. And TV2 is 6V1 plus 4V2. And I regroup to get -2 plus 6 is 4V1, and -2 plus 4 is 2V2. And now I go back. V1 is W1 minus W2, and V2 is -2W1 plus 3W2. And finally, regroup one last time. I get 4 minus 4 is 0, and I get 2W2. So the answer at the end of the day is the matrix with respect to the new guy is, let's see, I have TW1 is equal to W1 right here. So that is to say 1 W1 plus 0 W2. And TW2 is 0, 2. It actually wound up being a diagonal matrix. Here's the answer. So that was rather long-winded. I'm going to find a more efficient way to do it next, but let's look at what happened here. So really there were 3 steps. The first step was to write W1 in terms of V1 and V2. So right here, that was step 1. I wrote W1 in terms of V1 and V2. And the next main step after a couple of elementary things was to compute T of V1 and T of V2. Okay, so that's what I did here. T of V1, I plugged in T of V1 and T of V2. And then the last step was I went, after regrouping, I went back and converted the V's back to the W's. And that was step 3. And all of the other steps are just sort of rearrangements. And notice that step 1 had to do writing W1 in terms of V1 and V2. I used, let me just write them down. Step 1 had to do with converting W1 to W2. Step 2 had to do with writing down T in terms of the V's. And then step 3 was converting the V's back to the W's. Now, this first step, converting the W's to the V's, That's from this second, from the set of equations here up on the top, which I'll label 1. And writing down t in terms of the v's is this first set of equations, and writing the v's in terms of the w's is this third set. So each of the 3 steps corresponds to one of these sets of equations up here. And that's basically a hint to what's about to, how this is going to be sped up in terms of matrices. Okay, so I have those 3 sets of equations up here, and I have my 2 matrices. And here's the shortcut. So you take the matrix you started with, -1, 6, -1, 4, and you take this matrix here from this set of equations 1, pull out the coefficients and turn them into a matrix. I'm going to write down the matrix 3, 1, 2, 1. We make these things the columns, and put this on the right. And now go to step 3, take this set and write that as a matrix, which is to say 1, -1, -2, 3, and write this on the left. And the fact is that if you do this calculation, this will give you the result 1, 0, 0, 2. So that's an example of the main theorem, or the algorithm, which I've just demonstrated. And to say it another way, you start with your matrix, and you're going to end with your matrix in the new basis. And the way you got there is by multiplying on the right by this matrix C, which I'm going to call this matrix C. And now this other matrix is just the inverse, right? If you look at this other matrix that I used, it's clearly the inverse. So I took this matrix with respect to the basis B, and I multiplied it on the right by C and on the left by C inverse. And that corresponds to the 3 steps of the algorithm, which I wrote out. So that basically demonstrates the main theorem here. This is, I'll call this the change of basis theorem. And it says the following. We have a vector space, and we have a basis B, and we have another basis B prime. And let's suppose that we're given the matrix with respect to the basis B. That's just some given n by n matrix. And I want to compute the basis with respect to B prime. What I do is I write down this matrix C. And C stands for the change of basis matrix. And what it is you take the new vectors and you write them in terms of the original basis, and you make them the columns of a matrix. So you write down the W's, the ith column of this matrix is the matrix, the vector Wi written in terms of V1 through Vn. That gives you an n by n matrix C. And then the theorem says that the matrix in the new basis is given by C times the matrix, C inverse times the matrix in the old basis times C. So just to do an example of this C, in the one I just did, I had W1 was equal to 3V1 plus V2, and W2 was equal to 2V1 plus V2. So that said that C was equal to 3,1,2,1. Okay, so I just want to conclude with a couple of remarks. So the change of basis theorem says that these 2 matrices are related like this, TB prime and TB. So this is some matrix A, and this is some matrix B. So I'm going to forget about the T for now and just write this as A is equal to C inverse BC. So A and B are n by n matrices, and so is C. C is invertible, and this is just something about matrices. So now notice we can also write B is equal to CA C inverse. So here's the definition. If you have two n by n matrices, you say they're similar, A and B are similar, if they're related like this. If A is equal to C inverse BC for some invertible matrix C. You have to make it up or find it or something, but some matrix C, which makes this true. And the idea is if A and B are similar, then they represent the same linear transformation, just in different bases. So in some sense, they're the same, or at least similar. They have a lot to do with each other. They give the same linear transformation, just in different bases. And for example, I'll make a couple of comments here which are very useful. If A and B are similar, then they have the same determinant. They also have the same trace, and they have the same rank, and various other properties are shared by them, and all reflecting the fact that they are really talking about the same linear transformation in two different bases. So that's where I'll stop, and we'll pick it up next time.